Let's start out with what A is similar to B means. So that means B is equal to P inverse AP. So I'm looking to see that A squared is similar to B squared. I know. Since B is equal to this, how about if I multiply both sides by B? And if I multiply both sides by B, and then I'm just going to say that this is going to be B times P inverse AP. But wait a minute, what does B equal to? It's this, right? So on the left-hand side, I get B squared. Over here, I'm going to substitute this in, so I get P inverse AP times, so hopefully you can see this, times P inverse AP. Oh, look at that. I've got a P inverse and a P multiplied together. You know that that just gives us a 1. So I get P inverse, a 1, and then an A times an A. Oh my goodness. Look at what I've got. I've got A squared in there, don't I? So I've got B squared is equal to P inverse A squared. Oops, I put an inverse here. It shouldn't be an inverse there, right? I'm carrying along that P, which is here. I think I have it. I think I have A squared is similar to B squared. Okay, so let's look at this one. So we're trying to show that if two matrices are similar, then they have the same characteristic polynomial. So what I got to go to where you want to go. So thinking about, we need to show that the determinant of B minus lambda I is equal to the determinant of A minus lambda I. That's what it means to have the same characteristic equation. So let's start off with what we do have. A and B are similar. So A and B are similar means B equals P inverse AP. Okay, so let's go inside here. Let me try a different color here. Okay, let's go inside here. So what does B minus lambda A mean? Lambda I. B minus lambda I. And if I substitute this in, that would give me P inverse A P minus lambda. And now here's where I'm going to be clever. And I'm going to say that I can be rewritten as P inverse P. Why would I want to do that? Oh, look at this. This is pulling out a P inverse. So you know lambda is just a number, so I'm allowed to move lambda around, right? So I can factor the P inverse along. Maybe I'll just show you that. So I get AP minus, and I could rewrite it this way because lambda is a number. You can't switch order of matrices, but you can move the number lambda around. And so if I factor out a P inverse on the left, so what do I have? I get an A minus a lambda I, and then times a P. So I'm keeping that P there. Oh, wait a second. I think I'm getting close, aren't I? So I'm going to take this, and I'm going to say, okay, when I take the determinant of B minus lambda I, that's the same thing as taking the determinant of this, right? So I'm going to put in that P inverse A minus lambda I times a P. And then because of what you know about determinants, I can split the multiplication up. So I would get determinant of P inverse times determinant of A minus lambda I times determinant of P. And since determinants are numbers, I'm allowed to switch the order. So I'm going to move that one right here. So determinant of P, this one kind of just carries down the P inverse, and this one carries down A minus lambda I. And you know, look at that. These two turn into determinant of P inverse times P. And the determinant of P inverse times P is like saying the determinant of I, and the determinant of I will be 1. So we got there. So this equals the determinant of, determinant of A minus lambda I. Wow, that was challenging.